Okay, so previously we talked about Schrodinger's femboy and the two possible states or three possible states that the wave function can collapse to. So psi actual can either collapse to that or collapse to this one, which is the f or the m wave function. Or actually the norm. The norm squared. So what's this? And we also talked about putting, of course, Schrodinger's femboy talks about putting a femboy inside a closed space which we cannot peek into with a door in it. And we give him a tuxedo and a maid outfit, and then see what happens there. And that until we make an observation such as open the door and see which one he's wearing, we assume a superposition of both those states. And yeah, this is sort of a review of the last lecture, and probably even a review of femboyology. Okay, so today's lecture is going to be a bit different, maybe a bit shorter than you'd expect, because today we will be applying solving for the Schrodinger equation. That was lecture 1 or lecture 2. Sorry if my birds are screeching. But we will nonetheless solve the Schrodinger equation. We are gonna find the wave function of my friend, which keeps interrupting. You know that one guy that keeps interrupting my lectures? Yeah, we're gonna find this wave function. More specifically, we're gonna find, or using the likelihood that he has of getting a girlfriend, we're gonna construct the wave function of the state of his romance, or his affection. Oh, my birds keep screeching. It's annoying. Yeah. So let me just let that settle down. Okay. Okay. So, okay. I don't mind that. Okay. So, you guys recall that the wave function, or the wave equation, or Schrodinger's equation, is minus h bar squared over 2m times this is the time independent one, so times the spatial derivative with respect to x of the wave function plus v times the wave function. V is the force applied on the wave function. V is the force function, the weight function over this, and it's equal to some rate times the rate and time. And so that's equal to the energy of the wave function. Now, we're going to be using the standard quantum trap configuration here. So, since we're using SQTC, I know that my friend is not really a trap. He's a very straight person and like stuff like that. He gets the grossest stuff, guys. But we will be assuming that his mass is 1. 2. So that's h bar squared over 2. Partial derivative of this with respect to x times the wave function is equal to the energy. And we can package this out by factoring out this wave function, and it's minus h bar squared over 2 times the partial derivative with respect to x plus the wave function plus e to the, and then this is actually just the Hamiltonian operator, which gives us, now this is the force operator, this is the Hamiltonian. The entire thing is the Hamiltonian, which gives us the momentums. So this is h hat times our wave function equals e times the wave function. You notice that e here is not really, it's not hat, it's not expressed as hat. It's because in this case, when we're trying to find the wave function of my friend, we are assuming that the energy is constant and it is not a changing variable. So therefore, this is not an operator but a constant. Okay, and so in this case, because we're treating my friend not as light quanta, E is not equal to I h bar times the time derivative. E is not that. E is some other constant we're going to determine later. Okay. So Now this function here, another thing that in this state is that the force throughout all of these things, because we're independent of velocity or something like that, some abstract for velocity that's described in terms of romance, like affection or rate of affection. This v term here is 0. This vanishes because when we construct the actual problem, you guys will see that the velocities are 0 because we're only talking about position when it comes to these states. Okay, so just erase that v, and this is the equation we'll be using later. Okay, so let's now I'm gonna say it now. The probability of my friend getting a girlfriend after 5 attempts at girls is currently 1/32. So why is that the case? Now, primarily he starts with a girl, or he starts with one girl, and so he wants to woo that girl, right? So there are two possible ways of him, or there are two possible end states that his wave function can collapse into. So that first one is that the girl says yes, and the other one is the girl says no. We're gonna say that yes, or the x value for yes, or when we want to find the wave function at for the yes option, we're gonna say that that wave, or the value for that wave function is at 1. And for no, the x value for that wave function is -1. Okay. And the yeah, and so the wave function gives us the probability, right, of getting yes and a no. Okay, so okay, we start with the first girl that says no. So thus far he's had 5 girls reject him. That's kind of sad, but yeah. I know it's kind of evil for me to talk about this. It's like a bit it's a bit of a dick move, but I'm an evil person and I do this shit for fun. And it's all a joke, really, in the end. Please don't use these lectures, as I've stated countless of times in this channel, do not use these lectures as a weapon against other people, okay? All these lectures are just jokes. Well, they are 50% jokes, the other 50% serious, because we want to get the math right here. So yeah, and for that 50%, please correct me if I'm wrong, especially in the comments. We cannot promote a healthy learning environment if we only teach errors. So if any of you guys, any of my viewers are mathematicians here, or physicists that actually know a lot about this field, please correct me. Okay, so nothing over. So from the first one, we get another girl. So the second girl is either a yes or a no. So I'm going to use yes for y and n for no. And then from these two, of course, you have their branching out. So this is G1, this is G2, and then all the way down to, well, G6. Now you notice that this G2 splits off to 4 options. And you notice that this G2 is actually 2 options from 1. So if n here is the amount of possible states that we end up in for this given generation, or this given stamp in time, or given girl, the next one is basically just 2 times that previous amount. So if this is 1, this is 2, 4 is 2 times 2, and then of course when we branch this out to yn, and yn to get generation 3, or 1, 2, 3, 4, we get 1, 2, 3, 4, 5, 6, 7, 8, and then 5 is 16 now, and then the 6th one is 16 by 2, which is 32, and that's how we arrive at 32. Now, 32 in the denominator, you'll notice it's only the denominator. And why is that in the denominator? Why is there a 1 over it? Well, that's because we only have one possible thing that the girl can tell him, which is, no, I don't want to be your girlfriend, and yes, I want to be your girlfriend, please. Yeah. And because we can only pick one choice from both of those, we can only have like a 1 in a 32% chance that he would either get a yes or a no. So the probability that he get a y and an n is 1 in 32. Now, if the probability is just a yes, that is a 1 in a 16 chance, because we have a binary choice this time. So it's 2. And yeah, if we pick y and n at the same time, right? If we get both y and n, it would be 1 over 16. But I want to emphasize that these two, even though what I'm saying and doing is evil for my friend, I want to make it fair for him. So I want the chances of him getting a yes or no to be equal. So the p of y and the p of n is 1 over 16. So actually not 16, but 32. And this is just a packaged way of saying getting y or getting n. So getting rejected or accepted. And there's a 1 in 32 chance that he's gonna get both of those, or gonna get one of those. Because of course we can only pick one choice from this binary, with this binary pair. Okay, so now this is our starting condition. So this is our initial condition for when we try to find our wave function. And that is, if I have r here and another r, this is 1, this is minus 1. Then both of these guys at 1, the probability is 1 over 32. I know that's a very small value, like it's supposed to be like somewhere over here, like very tiny, but let's make it bigger than. So you can already envision that their wave function probably, my friend's wave function probably looks like this, right? Or at least the norm looks like this. Or their wave function was something that's thinner, but nonetheless like that. You can already think that maybe that's what the wave function looks like, and you'd be right. Okay. To think that. Actually, yeah. The wave function though, the slightly shorter the hills that you see in there are in C, not in R2. Okay, so yeah, recall the Schrodinger equation from that I said a while ago. So what you guys notice from here, so H bar. So I'm gonna go first with the analytic version of finding wave functions, because right now I have 2 wave functions that we can construct for my friend. There's one involving sine, and there's another one involving a Gaussian distribution. Nonetheless, both of these guys satisfy, should satisfy at least. I didn't check for the sine version, but for the Gaussian version, I would check. That does satisfy the fundamental property that the integral from minus infinity to positive infinity with respect to x of the norm of the wave function is equal to 1. This is a very important property that every wave function has to satisfy. And I believe the sine satisfies as well. I already normalized the sine function. I found that a factor at the end that allows us to converge at 1 over 32, or have the probability converge at 1 over 32 at 1 and minus 1. And as well, when we take the sum over all possible stuff, like maybe yes, absolutely no, no, those states which are like somewhere in between minus 1 and 1, and outside the bounds, or outside those two, 1 reaching to plus infinity and minus 1 reaching to minus infinity. When we take the sums of over all of those states and their corresponding probabilities, it should become 1, because I already normalized the function. Now I could be wrong with my normalization. I didn't check, for Christ's sakes, because it took so long. And I just wanted this to get over with. So if you see it, or when you see it later, when we get to it later, please check. And I guess I'll leave that to you guys as an exercise to verify that it is indeed a proper wave function and not just some stupid wave function. And just a disclaimer: when I do state the other wave function that I obtained experimentally and not analytically, like I just kept guessing, and tweaking it, the Gaussian distribution. When I did evaluate this integral, it didn't quite sum up to 1. It actually did sum up to 0. So there might be something wrong there. I could very well just, add 1 to the function to normalize it, but yeah, it's a bit strange that it didn't quite give 1. So yeah, I guess we'll just get to that when we get to it. Okay. So yeah, fundamental property that all wave functions must satisfy, and surely the sine one that we will derive will satisfy. So our new Schrodinger equation is h bar squared over or minus h bar squared over 2m times the spatial derivative with respect to x of the wave function equals the energy of the wave function. So, unlike femboyology and other lectures before here, we're not gonna assume that my friend's energy is 0 or 1. We're not gonna assume his energy is 1. Okay. We're gonna assume it's some constant that we're gonna determine here. Okay. And in fact, there will be 2 energies that we will determine for him, because what we're gonna do, instead of thinking or trying to construct a wave function for both 1 and minus 1 as a whole, we're gonna split them into 2. So this lecture is in 2 parts. Or actually 3 parts. We're gonna first compute the wave function of the minus 1 and wave function with 1 as the boundary condition, right? And another thing that we need to note is that, of course, I'm restricting this thing so that once you get to 2, so 2n minus 2, everything else is 0. So the probabilities will all be other zeros. So think of it as a little bit more complicated version of the square well problem, or the infinite well problem, or particle in the box. But instead of a particle, we have my friend's love state. Okay, so separate this. If you notice, we can bring all of the variables to one side and all of the constants to another side. Or yeah. So if I divide both sides, or if I multiply both sides by 2m, I get as h bar squared x is equal to e psi 2m. And then I guess we divide by h bar squared, right? I didn't quite write down the derivation for this, but which way? Yeah, we're looking for. So yeah, just divide both sides by h bar squared. So we get the spatial derivative of big psi is equal to e psi 2m divided by minus h bar squared. And then we divide both sides by psi to get, or actually, we can bring that psi to the outside part. And from here, I guess what we want to do is find a function that satisfies this criteria. And you'll notice that the second, this is not the first derivative, second derivative. 2. And notice that sine fits this really well. You can check that this, if we rearrange this just a little bit, you notice that e to m, yeah, we're assuming standard quantum trap configuration, so that's just 2, sorry, e2 over h bar squared minus h bar squared. And that is all just multiplied to the wave function. So we actually think of this as, let's say this is called k, okay? Let's set this equal to k. So this entire thing just shrinks down to d squared x of the wave function, sorry, italicized x, equals k times the wave function. So we want a function such that its second derivative is equal to just itself. And yeah, that is sine. Sine satisfies that this differential equation. So sine is a solution to this differential equation. So you guys can probably guess by now that our general solution is sine. Sine of kx. Where k is equal to, if we simplify things, we can end up with something that goes like this: the square root of 2 times the energy over h bar. So simplify things a bit, do some algebra here in the middle, and we get that. That's the general solution. Okay, so this is sine. And you may be wondering, well, it's sine, right? But how come it's real valued? Well, it's just for this case here, we're sticking with the real numbers for the time being. So all of this happens in R2, okay? And you notice that yes, indeed it happens in R2 because E is not equal to IH bars, H bar times the temporal derivative of the wave function. So E is not necessarily energy operator, but is a constant that we want to determine. So all of this exists in R2 right now. So yeah. So this is our general solution right now. What we want to do is think about it. Let's think about it. Okay, let's construct the problem as a picture. So this is our x-axis. This determines whether at this point we get a yes or a no from the girl. This is the y-axis, which determines our wave function. So this wave function psi is a function of x, of course. Now, at 2 and at -2, we want it such that there's a wall here. And then everywhere else, that's infinity. So it's a particle in a box problem. So this is the origin O. And then this is 1, and this is -1. -1, not -2. -1. Now, you'll notice that for sine, I'm going to erase the bottom parts here for now. That's why you guys should remember, okay? You'll notice that for sine, it goes like this. And that may be a bit of a problem because we have a negative probability. Well, we could just take the absolute value of sine. But let's ignore that for now, because when we do take the conjugate of this, or when we square this, when we take its complex conjugate, we end up getting a flipped version of sine. That's all positive value. Okay, so yeah, even though it's real valued, we still have to square it and treat it as if it's a complex valued function. So yeah, gives us that. Okay, so this is what sine will give us. Now you'll notice that when we travel along a sine wave or a cosine wave, it's like traveling around the circle. Okay, a half travel around the circle is pi radians, or 180 degrees. Okay, 1 radian, as you notice, is pi over 180 degrees. And a full rotation around the circle, which corresponds to a full cycle of this, a full travel along the cycle of this sine function, is 2 pi, or 360 degrees. I'm going to use radian notation here because that's more sensible math and more compact. And it's more widely used anyway. So this entire thing is a 2 pi radian travel. So this is practically, this over here is practically, this 2 and then -2. But we want it such that at sine pi radians, or pi over 2 radians, or 2 pi radians, we want it such that this is precisely 0. Okay? We want it such that it's precisely 0, and all the other outputs are 0 as well. We want it such that it's like that. So you notice that, of course, we just set sine kx equals to 0. And then find the kx that equals 0. That gives us an output of 0. And you will notice that kx, of course, is equal to 2 pi. Because sine 2 pi radians is 0. But at the same time, you notice that, k is actually 2e over h bar. So it sort of becomes like this. So yeah. So pi now is equal to 2 times the energy over h bar. So that's pi, and we just simply plug this into what we perceive to be a solution to this relation. And then we square both sides to get rid of the radical sign. So after we find this or establish this relation, we want to find the energy. We're trying to find the energy now. So square both sides. So pi squared is equal to 4 times 2e over h bar squared. And then rearrange that again. Pi squared equals h bar squared equals 8e. And then just divide both sides by 8 to get e, the energy is equal to pi squared times h bar squared over 8. And when you look at the generalization of this problem, if we set this minus 2 and positive 2 value to a, you notice that this is actually equal to, or this implies the generalized form, pi squared times h bar squared over 2a squared. Plug a for 2 and we get 4 squared times 2a. Checks out. And in fact, you notice that this a here, this is above, this a is above over here. And half of this is just pi, right? Yeah. So that's our energy. Or at least for the first case, for this positive part. For the negative part, the energy is just this entire thing, but minus 8. But the thing is, okay, when we do have a minus here, we notice that this is actually a minus 2, right? Because this is a. Now, because it's a minus here, because it's a minus, when we do carry on over and square it, it still becomes minus, or it becomes a positive one. But this 8 here stays negative. Yeah. Or actually, I think it becomes a positive because when we do square that, it becomes positive, and then yeah. And when we do square it anyway, so it doesn't matter. It gives us the same energy. Now, I said in the beginning that the energy could be different, but we actually just showed here that it's the same. So pardon me for that. So the energy is pi squared times h bar squared over 8. Where of course h bar squared is reduced Planck's constant. Okay, so now that we found our energy, I suppose I'll clear up the board, let my bird settle, and then we will again list it up here, the energy, and then we will continue trying to solve for the analytical condition. Okay. Okay, now you will notice that, oh wait, yeah, we got this already. Here it is, we have k, we have e, but how about when we want to normalize the wave function? Okay, what if we want to normalize the wave function? Oh, I forgot to state a while ago, the reason why it came to be like this is because, you noticed a while ago that it's 2 pi, right? So we divide both sides by 2 and we get 2 times a squared. Okay, that's that. because we're focusing about a full half rotation. Okay. All right. Now the thing is, all right, we got our answer here. We got our general solution, or actually a specific solution for this problem. But we still want to normalize it because this isn't normalized. If we try to graph this, of course, and then take its integral from infinity to positivity of its complex conjugate times itself, this would give us a different value. So we need to normalize this. And in fact, if A is of course our bound, the bound that we want it to be in, the normalized version of this function is the square root of A over 2 of course our regular function. That's the normalized version. And the reason why we normalize it is because, okay, we take its complex conjugate, and then we get something that's like a over 2 of sine kx, right? When we evaluate it, we get something like, or if we just evaluate the sine kx here, from minus infinity to positivity, given our chosen values, we get something that's 2 over a. So we want a value, or we want something at the front of our function that's just a constant, right? Such that when we do evaluate the integral, when we multiply those constants, it vanishes to 1. That's the concept of normalization, as I stated in its separate lecture. So that's square root of a over 2. And actually, you'll notice that this wave function is precisely the one that I used during those lectures. And that's because this wave function is the easiest to work with, and the most intuitive to work with you guys. I could very well use a different function like cosine. I can use e to the ikx. And in fact, I believe I will in a future application, but just for the sake of the simplicity of this lecture, we're going to stick with this wave function that I use all the time. Okay? So yeah. And if you plug in a here to be 2, you'll notice that it just vanishes to 1. So we practically don't need to normalize the wave function. However, the weird thing is, for minus 2, this becomes I. So it becomes a complex value function. But I don't think that's much of a concern, because when we do take the complex conjugate of it, and then take its norm squared, then it would become real value. So yeah. But we want to focus on the real part. So really, plug in 2 over here, and then we get just 1, because that's 2 divided by 2, 1, square root of 1 is 1. So we practically don't need to normalize it, because it's already normalized for our case. Okay. So yeah. So I suppose now the new wave function, because this is just the first wave function wherein 2 is, or where a is 2. We want to know the wave function for when a, or the bound, is in the minus part, right? So 2 is just, well, sine kx, same thing, but of course a is equal to minus 2. And the full wave function of my friend, psi actual, is just psi 1 plus psi 2. So this is the wave function of my friend. Now you can make this cosine, wouldn't matter, same thing, would solve the equation so long as it has the same constants. And yeah, so that is the analytic way of obtaining my friend's wave function. And okay, now you may be thinking, okay, yes, you got this right, you got this wave function, but how am I certain that at 1 and minus 1, this entire thing would actually vanish to, or actually its norm squared would vanish to 1 over 32, as we said, getting a yes and no would give us a 1 over 32 probability. How do we get that probability? Well, because this thing vanishes, or its norm squared vanishes at 1, then all we have to do is just plug a certain constant. And so to do that, what we did was say, okay, I have an a. Now, just plugging 1 over 32 at the front of the function doesn't do anything that we want it to do. It would give us some other value. So what we want is put an a at the front of the sign, and then, state our necessary values. square root of 2 times the energy over h bar x, and then set it to 1 over 32. So what we're doing here is modifying the function, right, or finding a scalar for the function such that we have x values that diverge or have an output of 1 over 32. And you notice that, okay, pi x here is 2, because of course we want it such that at 2, or at the output 2, this entire thing is 1 over 32. Okay? Yeah. It's always been a bird obnoxious that my bird screech, so excuse that. 2. So this is 2 at the front. So it's 2 root 2e equals 1 over 32. And then I suppose what we just do is a is equal to just take we can always take the arc sine of this, but the thing is we need to take the a out. So actually the value I solved for here is kind of wrong. Yeah, I realized it just now. So let's solve this here on our own. So 2 here, the sine of all of this is equal to 1 over 32. So I guess we don't really need to take the arc sine, so it's just divided times 1 over the sine of 2 root 2 energy over h bar. So that is the term. So that is the term that we put in the front of our wave function, such that at 2 we get 1 over 32. And let's solve for also if we have a minus 2. Square root of 2e over h bar equals 1 over 32. And same thing, but instead we have a we have a minus 2 here. So a2 is 1 over 32 times 1 over sine of minus 2 times the square root of 2 times the energy over h bar. And just to verify, energy is pi squared times h bar squared over 8. So this entire thing is a constant. And it would be measured in radians, supposedly. So the sine of minus 2 over the square root of 2e, or 2 times energy, over h bar. Put inside the sine function. So that's the a term you want to put on top or in front of these two functions. And then correspondingly, there's sum in order for us to get 1 over 32 at 1 and minus 1. And so the real final wave function is not just those, but those times this. So actually, let's just stick 32 in front of that. So 1 over 32 sine of minus 2k times the first wave function plus the second wave function. And this, ladies and gentlemen, is my friend's wave function, or the wave function of my friend's love state. Okay, yeah, this was a really it's an computation, but this gives us two sine waves here. If we just isolate it to one, we get one component, and another one, we get another component. And so supposedly, when we do take the square of the norm, you would get 1, or the sum from minus infinity to plus infinity of the square of the norm of this wave function, we get 1. And to do that, we just need to split this among here, just distribute it, and then evaluate the integral correspondingly to each term. Okay, so now that we have the analytic version, just to close off the lecture, let's do I'm going to show you guys the experimental one. The experimental one could very well be very wrong. In fact, both of these could be very wrong. Like, I did something very wrong in my computations, but here's what it is. So what I mean by experimental is that I went on to Desmos, got a got the usual Gaussian distribution, which is e to the minus x squared, and then I tweaked it. A lot to satisfy our conditions, and then sum them up. So yeah. So that's that. So the experimental version, which is roughly the same, looks like this. And you'll notice, oh, it already looks pretty okay. It looks like what we want it to look like, right? And then this is 32, rule number 32, 1 minus 1. And the wave function for this, the experimental wave function, so this is the experimental version, actual of my friend, is 1 over 0.055389182848 times 1 over 32 of e to the minus x minus 1 squared plus 1 over 32 e to the minus x plus 1 squared. This is the experimental version. You guys can plug it into decimals to check that this is correct, or probably true. That indeed at 1 and minus 1 we get a 1 over 32 probability or output. And so that ends today's lecture. And yeah, so thank you for watching. And my friends are probably, you guys are probably watching this. My friends, this is very thing. I just wanted to do it this morning, and then I just wanted to get it out here. It could very well have a lot of errors. I'm not that confident in my work or that arrogant in my work. And I urge you guys to check these guys. So that's a good place to stop.